Today I'm talking to you about sea level rise. We can make it informal if you guys wanna, you can interrupt me if you want with questions, or wait until the end, and that works too. So sea level is changing in Maryland. It's been changing for a while. And I just have some nice pictures here to sort of illustrate that point. But there is this presentation is basically sort of trying to summarize a little bit the 2018 sea level report for Maryland. Maryland, actually, the legislature requires every 5 years a report on this topic. My institution is mandated to be in charge of it. We get people not just from our institution, and there's a variety of authors here. This is the author team. We get experts to help us if we don't have the expertise. And I want to highlight Bob Kopp here at Rutgers University. His mother is actually a legislator in Maryland, but he's a professor at Rutgers University, and he is an extremely well-regarded sea level expert, and did a lot of contributions to this report. So I highly recommend that you go look this up, and the next one will be produced in just a little bit, 5 years from 2018. So sea levels are rising globally. We have data that shows that. So this is the satellite record of sea level rise based on satellite altimetry. And we see the change in mean sea level has been going up. This is in millimeters. Over the time period of record, it's gone up about a little over 60 millimeters, 6 centimeters. Sea levels are also rising locally, and we have some of the longest tide gauges along the eastern seaboard here. Baltimore is nice and long. They show a rate of sea level rise somewhere in the 3 plus or minus millimeter per year range. And the problem with all this sea level rise is it actually impacts us. Obviously, if you live on the coast at low elevation, you notice it. But if you are in Annapolis, you really notice it because their downtown waterfront floods pretty regularly, to the point of being a significant economic loss for businesses downtown, parking areas, and yeah, for the city in general. They lose revenue when they have flooding downtown. So it's becoming a serious problem, and that's part of why Maryland takes it seriously. But what's causing all of this sea level change? There's multiple causes, and so I'll kind of go through what some of the causes are. Obviously, melting ice at high latitudes will get us some sea level rise. You can raise sea level by melting ice. So the ice sheets up in Greenland, in Antarctica, are losing mass, and so we have rising sea levels. The other way to melt or to raise sea levels is to melt other ice, and so ice over mountainous regions, and we're losing glacial ice on mountainous areas at a rapid rate. Then the third mechanism for raising sea level is grouped as two things: temperature and salt. So the Earth's oceans are, well, they are rising because they're warming and because they're getting fresher. Because when you warm something, it expands, and that's what happens to the water molecules. And so with that much volume of the ocean, it actually is a substantial impact. Salt is a little different. When you add salt, the salt dissolves into the water, and it actually squeezes the ions, squeezes the water atoms closer together. And so when you add salt, then the density increases, your volume decreases. But when you freshen the ocean, then you end up with that water taking up more space. There's less salt in it. So so when you melt all those glaciers, you're adding fresh water, and that freshens the ocean. So we call the combination of heat and salt steric. So when you talk about, when you might see steric sea level rise, they're really just talking about heat expansion and the impact of freshening. The fourth main thing for changing global sea level is tectonics. So the Earth, this is a geologically leaning group. So tectonics are really important for long-term height of the seafloor, and that determines how much volume your ocean basin has. And if your ocean basin has less volume, then you're going to spill over onto the continents. So sea level changes on millions of years timescales because of tectonics. That's less important for modern change. The other melting ice and steric effects are much more important. But there's global sea level rise, and then there's local sea level rise. Let's talk about some local effects here in the mid-Atlantic. So I've already mentioned glaciers, polar ice, and steric effects, is heat and salt. But what's next? Strangely enough, gravity. So when the ice sheets at the poles are large enough that they have a substantial gravitational attraction that actually pulls seawater towards them. So when they start to melt, that mass goes away from those centers and is more distributed, and therefore the surface of the gravitational surface of the ocean actually changes a little bit. It's a little bit lumpy normally, and it still is lumpy, but it's lumpy in a different way when you reduce the gravitational pull of those ice sheets. And we just happen to be in a part of the ocean that rises when you melt the ice caps. And there are other places on Earth that are affected that way. There are other places that get the opposite effect. The next one I want to talk to you about is regional ocean dynamics. What does that mean? So that's this red arrow in this pretty plot. And that is really the Gulf Stream. So the Gulf Stream screams by here really fast. It's a fast moving current. It's a lot of water. And we're on a rotating planet. And there's some strange features of rotating fluids. And you can imagine a situation that's very analogous. So think of a bucket. Put your hand in the bucket, and the bucket is full of water. Put your hand in the bucket of water and stir. When you stir, you're going to have the edges of the water are going to raise up, and the center of the water is going to have a little divot in it. And that's because it's rotating fluid. It causes this tilt. And for very similar reasons, the Gulf Stream passing by us tilts the surface of the ocean. And so one projected feature of future climate change is that the Gulf Stream likely will get slightly weaker. And that will actually cause the surface of the ocean to relax a little bit, and thus sea level will rise on our shores. So it's a local effect because of this big global ocean circulation that happens to run past our shore. So these are all different ways that sea level rises around here. But when you talk about sea level rise in any particular location, we're talking about relative rise. So the land can also sink. And there's a few ways that that's happening as well. So let's see, let's go to the next one. Yes, groundwater extraction, that's the next one. Down at the bottom of the screen, you see these little dashed lines. And this is a picture, or I guess a cartoon of water being taken out of the aquifers. And basically, once you take that water out, the interstitial space of the geology basically starts to settle. We're on unconsolidated sediments here, really quite deep, and it will cause settling, and the land will subside, will lower. Another similar process is just compaction of sediments. As I mentioned, we sit on top of a very thick, unconsolidated wedge coastal plain that's been coastal plain for a good long while, unless it was covered under the ocean, as you all know. So basically there's compression of those sediments that will happen over time. It happens a lot on the Gulf Coast, but it also is happening here. The third way that we are reducing our land height, well, we're not doing it, is what's known as glacial isostatic adjustment. So that requires a little explanation. During the last ice age, there was a big glacier on top of Canada, essentially, top of North America. And all of that ice weighed a substantial amount, enough to flex Earth's tectonic plate underneath it and cause the plate to subside underneath the ice, but a forebulge in front of the ice rose up, and the mid-Atlantic happens to be on that forebulge. And so now that the glaciers of the last ice age melted 10,000 years ago, that forebulge is slowly relaxing. So it's adjusting. So that's, these are the causes that affect sea level in our region. And the sum total of all of these things that are not global mean that the sea level in the mid-Atlantic region is rising ever so slightly faster than the global numbers. So it's still small, but we get sort of the short end of the stick when it comes to sea level rise. So what's going to happen in the future? That's sort of what most people want to know about. This is where Bob Kopp's from Rutgers University research comes in, because what he has done is create probabilistic modeling of all of these factors. So what he's done is he said, okay, we know glacial changes plus or minus this number. We know polar ice sheets plus or minus this number. We know gravitation on plus or minus this number. So he takes all of the uncertainty bounds and very rigorously mathematically adds them all up for everywhere on the globe to make a sea level projection for everywhere, basically, for a global sea level projection, but it's not a global average. It's a spatial data set, and that gives us, specifically for the Mid-Atlantic region, this is particularly for Maryland, our projections of sea level rise based on the global expectation plus the local, the smaller variations due to the local situation. That's what I'm showing you here. This is particularly for Baltimore. We had to choose a site on the Earth to make this for. And for the Maryland report, this is from the Maryland report. So just to orient you to this figure, we've got time on the bottom axis and relative sea level rise in feet. I will apologize that sometimes this talk has some metric numbers because I think in metric and I don't even notice that they are. And then for the Maryland report, we made sure it was in imperial, just so that we could communicate to the largest audience. And then we have this this bar that indicates possible sea levels at any given time. And they're in different colors. So the different colors represent possible, the RCPs are representative carbon pathways. This is a potential way that human society could evolve, and just with blue being a more aggressive carbon reduction, green being some progress towards reducing carbon emissions, and with the orange as sort of business as usual. So right now we're on the orange track. We haven't changed from the orange track yet. Although actually I should say that I have not looked closely. Well, I have looked at, we have some reduction because of 2020 being 2020, but it's at this point, we don't think it's gonna continue. We'll have a little dip in emissions just because people sheltering in place during COVID, but it's not a big change from a climate change perspective. But so right now we're effectively on the orange track, even if we might have dipped in recent months. The other thing to explain is what these percentages are. So essentially, with the sort of median estimate here, you have a 50-50 chance of being higher, you have or lower. This is sort of the middle of the road estimate. And then we have with this 5% level, that's the bottom of the bar, you have a 5% chance that sea levels will be lower than that. But you have to remember the converse is that a 95% confidence that sea level change will be higher than that at that time. And similarly, at the top, the 95th percentile there, you have a 95% chance that sea levels will be lower than that at that time. So the most likely range is this darker area, so that's highlighted. So what are we looking at? We are currently locked into a certain amount of sea level rise just because of the emissions that we have already put into the atmosphere. They've gone into the ocean, they've gone into the biosphere, and when if we stop right now, no more burning fossil fuel as of today, those sources would actually emit back into the atmosphere the stuff that we had put in. So it would take a little while to change things. But it also means that if we stop today, there's nothing we can do about a certain amount of change that's going to happen as the system equilibrates to the carbon that we've put in already. So we've got this sort of gray bars for it doesn't matter what we do, this is what we're getting. And so we're guaranteed pretty much 1.5-ish by 2050. The question is what happens in the future, and that's where we have the power to change what's going to happen. And most of the projections have gone out to 2100 because we started doing this at the end of the 20th century, started making these projections, thinking into the future. And 2100 seemed like a good, like it's about 100 years in the future and we're gonna start this. We're gonna like sort of use this as a benchmark. But I think now that we're at 2020, 2100 isn't that long. That's my daughter's lifespan expectancy. Her life expectancy at birth is right 2100. So that's my daughter. Like she's here. It's very real. And so now we started also putting a little further projections further back. So 2100, we're in the business as usual, we're about 3 feet. It sounds like it could be uncomfortable. However, one of the things that's not being considered in this projection is Antarctica. Antarctica has, in these sea level projections, been such an uncertain quantity that we just ignore it. Well, we don't ignore it. There's plenty of people studying it, and particularly studying the ice dynamics, because how large ice sheets melt or don't melt is really key for understanding or for projecting future sea level change. So something you need to understand about Antarctica, it's a desert. So if you warm it, it's going to actually increase the moisture in the air, which will increase precipitation and increase snow and therefore moisture storage, ice storage on Antarctica. When I was in graduate school 20 years ago, I remember being told by a professor, we're not worried about Antarctica for sea level rise, because it was considered a positive, because if you warm it, you'll have moisture there, it'll get more ice, we'll be storing more of that liquid water up on the ice sheet. So it's not contributing to sea level rise. In fact, it's helping. Science has changed in the last 20 years. So we're a lot more concerned about Antarctica now. And this is the reason. So on the top left, there's a map of Antarctica by elevation. The blue shading, is below sea level. There's a lot of Antarctic ice that is below sea level. And in fact, it's most of the West Antarctic ice sheet. If you compare to the plot below, the West Antarctic ice sheet is substantially below sea level. And it's not particularly stable because of that. The East Antarctic ice sheet, that's where it's going to store a lot of moisture because it's warm. So the East Antarctic ice sheet has about 60 meters of sea level. If it were to melt, that would be very scary. The West Antarctic has 3 meters or 10 feet of sea level. And now we're talking things that might happen or that could happen. So the question is, how have polar ice sheets behaved in the past when the Earth has warmed? We've come out of glacial periods. We've been in warm periods before. So that's where my geology background comes in, because that's something that we can address. We have plenty of evidence for past high sea levels. I put this slide in because you guys know of one of a great source of evidence for higher sea levels. We're on a passive margin of a tectonic plate here in Calvert County. And so tectonics are not raising and lowering the land hugely. And yet we have marine fossils high on the cliffs. That's because that's where sea level was, way up high. And so during the Miocene, when our cliffs were underwater, the Earth had no Greenland ice sheet and very little Antarctic ice, much less than today. There's some nice evidence of changes in sea level, but there's other evidence. So corals are such evidence, fossil corals in particularly, because we have there are certain species that prefer the very high light, high energy surf zone. It's this on the right, Acropora palmata, that sticks up a characteristic sort of shape. You can recognize it in fossil in situ situations in outcrop because it has that angle to it. And here, this is actually me on the left with a fossil reef. This is actually a different species, but next to an approximately 90,000-year-old coral. And that's a pretty big coral head. You don't see those today. And that was in 2019. I was just so happy I did that trip before COVID. So this is, Barbados is a place where a lot of the research has been conducted to understand sea level change, because they have corals growing on this island, and essentially the island works like a dipstick, where the sea level changes and the corals grow at each change time. And you can look at the elevation of the corals, and you can get at and the age of the corals, and you can reconstruct sea level. So Barbados is not the only place this is done. And recently, well, not too recently now, it's been a while now, but the latest compilation of such data is here. And all of these little blue dots represent a coral of known elevation or depth below sea level in some cases, and a radiometric date. So you've all heard of carbon-14 dating. We use uranium, thorium isotopes, much like radiocarbon. It's a radioactive decay series. So we have a lot of data, and if you look at this is the last 35,000 years. So on the left is present, to the right is 35,000 years ago, and at about 20,000 years, that's the last glacial maximum. So that's when it's the depths of the last ice age, when sea level was at its lowest. There was the most ice up on land, and we came out of that in a series of sort of pulses. This one right here that I've labeled is meltwater pulse 1A. There's 1B, it's over here. And we think these pulses might be collapses in the West Antarctic ice sheet. So there's debate about what causes the big pulses, because these are very fast sea level rise. This is 40 millimeters per year. And just so that you get a context for that, over the last just sort of from about 17,000 to 4,000 years, this basic slope here, when we came out of the last ice age, sea level rose at 9 millimeters per year. And today we have about 3.4 millimeters per year. So sea level has risen in the Chesapeake Bay area about a foot in the last 100 years. And you see that when you take hikes in the coastal zone. You'll see these forests that are basically dead with a very swampy coastal marsh right next to it. And it's because they flooded. This was low-lying forest that flooded in the last 100 years. I bet if you radiocarbon the trees, it would be in the last 100 years. But so we see that evidence of sea level rise, and that stuff was natural for the most part. And what we're looking at is could be much worse if things get bad. Well, let's just say that. Previous projections of future sea level rise were ignoring Antarctica because we couldn't even begin to model it. The geologists were sort of complaining loudly that that we needed to take into account Antarctica. And finally, a few years ago, there was a really pivotal paper that showed that they were able to use some basic ice sheet physics that had been finally figured out, and be able to model historical ice sheet behavior. Historical meaning geologic history. And so that enabled Bob Kopp to revise his probabilistic methods of estimating sea level rise, taking into account Antarctica. So, so the last time I showed you a figure from the last time I showed you a figure from the state report, I showed you some bar graphs, and those are essentially, those are summarized, the median line is summarized as these dashed lines. Now we look at the difference between an aggressive greenhouse emissions reduction, a middle of the road greenhouse reduction, and a business as usual. And suddenly the stakes are a lot higher. We're talking, in my daughter's lifetime, we're up at 6 feet, and it just gets worse from there if we don't do anything. The break point here is about 2050. That's when things will start to matter, or at least that's what the data show right now. And the higher rates here that Bob Kopp found in his revised projections are much more in line with the rates of sea level rise that we see during the deglaciation. And that makes sense because we are perturbing the system by adding carbon at a very high rate. So you expect that the sea level would respond with at least a similar intensity, if not worse. But one could argue that the ice sheets are smaller today than they were in the past. So maybe there's less inertia, or no, I shouldn't say inertia. Less possibility for rapid change. When you're sort of perched on a precipice, you've got a long way to go. If you've got tons of ice, then you can get rid of it fast. But if you have less ice, it might be a little slower to come off. But either way, that the finer points are somewhat irrelevant. What's important is that when you include ice dynamics from Antarctica, you get a lot worse projections for the future, and it really highlights the importance of reducing our emissions quickly so that we avoid such things. So what could happen here is a map of just sort of parts of Maryland. This is the Eastern Shore, and we are that dot. And Solomon's, well, I shouldn't say we, but if we were in person, we would be under that dot in Solomon's. I want you to notice that Calvert County doesn't change. We'll look at some sea level rise projection for the future. Eastern Shore is going to change a lot, and so will the Maryland coastal bays area. And I highly recommend going to this website, climatecentral.org, and they've actually they've worked with Bob Kopp on this, and they are a very science-based organization trying to get the word out about what the consequences of climate change are. So they have this great sea level tool that you can play with to see what areas you're familiar with, and what will they look like. So under a business as usual scenario with Antarctic ice modeled, you get about a 6-foot rise, and that would take out much of the Eastern Shore and the barrier islands. If you notice, Calvert County doesn't change that much. We've got those nice cliffs that we have highlands. So aside from some communities like Solomon's, Brooms Island, other low-lying communities in the county, we are pretty robust. I will tell you that you don't have to raise sea level very much to have much of the Blackwater Creek area here in the center part of the figure go under. It's very close to sea level already. So the question is will we continue like ostriches, or will we be matadors and face our fears? So I don't want to be totally pessimistic. I think we have a lot of power to change this, and we just need the motivation to do so. So this is my motivation. And what can we do? Inform yourself first. You're here, invited me to give a talk. Demand our politicians address this issue now. And the question is how, and that depends on your political leanings, and I do nothing about politics. But the science tells us that we need to reduce our greenhouse gas emissions as fast as possible, like yesterday. And then if we need to be at net zero by 2050 to avoid some of these really catastrophic changes. So how do we need to go about doing it? Well, we need electricity generation that is carbon neutral. How you get there, that's again a political thing, but that's something we need. We need some sort of transportation that's carbon free, which at this point the technology is such that electric cars are the only viable option that I know of. We need the infrastructure for it. We need to reduce our agricultural emissions, and that's on a global scale. So the US actually has fairly efficient agriculture, but we have a ways to go in terms of optimizing our food production for greenhouse gas emissions. And similarly, we need to help other countries do that. And we also need to transition to clean manufacturing of some sort. If we want to be able to produce goods, we need to be able to do it in a cleaner way. Things that you can do, I highlight the bigger things because these are things that your individual is not going to do. And we need to make sure that we put pressure on our politicians to make sure that these things need to happen. Again, how they happen, that's a whole nother matter, and that's a political thing. But scientifically, these are just like, in order to make our system function, our society function, we're going to need to do this, and do it in a carbon-free way. But personally, we can change our personal habits in the near term, while we wait for larger things to happen from a policy standpoint, and reducing your transportation fuel use. I want to highlight air travel. Many climate scientists have stopped flying or considerably reduced their flights, because for many of us, we've already done a lot of the personal reductions that you can do. But it's the flying I've done my personal budget, and it's the flying. Planting trees is huge. That really can help. The key is to make sure that they'll be able to grow in that spot for a long time, because that's what's going to soak up the carbon. So with that, I will end the show, and I am happy to answer questions.
Great, thank you very much. So if you have any questions, don't hesitate to ask them now. I have a question actually that came to me during your talk, Hali. So in that map that showed the Delmarva Peninsula flooding significantly, so that was slide number 11. Yes, so you could see that the width of the Chesapeake Bay increases substantially. And you had mentioned that there wasn't much change to Calvert County in terms of flooding because of our coastal elevation. But what I do wonder is about the amount of erosion. So with that wide of Chesapeake Bay and with the fetch, the wind blowing the waves, I would think that wave energy would increase significantly, and and increase the rate of coastal erosion in Calvert County much beyond what it is at present. Has that been considered at all?
It has been considered. I'll tell you that I had a debate with Peter Vogt about what would happen to the cliffs and erosion under such conditions. But given that he's a geophysicist and I'm a marine geologist, neither of us really has the expertise to say. So he thought it would cause more erosion, and I thought it would, or I thought it would cause more erosion. He thought it would cause less. I don't know which. I will tell you that there have been investigations into the tidal range. And that's a colleague at Horn Point, actually, which is underwater in this picture, and has looked at the importance of basically not hardening the coastlines as sea level rises, because otherwise we're actually going to, if we harden our coastlines in order to keep back the ocean, we'll just make the tidal range larger, and that could actually cause more trouble. So I don't know specifically, but yeah, it's something to consider. I think it probably would cause more erosion, but again, a geophysicist would absolutely tell me I'm wrong. So.
Okay, thank you.
Even if I can interrupt, I'd just like to remind everybody that we have places along the Calvert Cliffs that are eroding at more than 2 feet a year, which is greater than the amount of sea level rise that we're seeing anywhere else in the bay. And so the point that you raise, I think, is an excellent one. And if anyone wants to learn more about it, if you look at some of the papers that Darren Lowry has done, he's a very, very big proponent that strongly says that wave action and erosion right now is causing more harm to the Chesapeake than is sea level rise. Both of them are issues, no question about it. But he says that it's actually the fetch. And that's what you're referring to, Stephen.
Yes.
The fetch is increasing, which means the wave action will also be able to increase. So erosion is going to increase.
I think that's a very key consideration. And also the potentially large storms coming through might change their frequency or intensity as well.
Where is your research going to take you in the future?
I have no idea. I'm trying to make a trip to the Keys in the Florida Keys in August, yeah. So my bread and butter research is really using fossil corals as recorders of their environmental conditions, particularly the temperature and salinity of the ocean, in order to understand tropical climate variability. The tropics are essentially the heat engine of the climate system. They get more of the sunlight. That's where the energy is. And the climate system fundamentally is trying to transport heat from the tropics to the poles. And so I mostly am doing trips to lovely places in the tropics. I have to admit, I have no complaints. It was a strategic decision when I was 18 to be able to scuba dive for a living. So yeah, I've been working. I went to Barbados actually to teach a course on sea level and climate change, and it was a field course. With Williams College. But then while I was there, I got also some samples for some research. So where to next, I don't know. I'm actually sort of in between projects, trying to wrap up some things. And unfortunately, lately, all I've been funded to do is data analysis, which pays the bills, but no fun trips.
Hali, if you don't mind me asking, in one of your early slides, you talked about the Gulf Stream, which is basically, that's only a piece of it that goes off the East Coast over towards England, part of it swings south, and you pick up another current that comes back across just above the equator, creating that swirl you were talking about that raises at the edges. I guess the question is, as it slows down, what's the expectation of the impact of that? And also, because as your analogy of the bucket, there's a certain hollow in the middle that might get filled up also, along with dissipating out to the sides. So is that really that big a impact?
Well, so, okay. I need to clarify my analogy. So the current is moving northward along our east coast, and that actually tilts the sea level, I guess, towards us, so it's lower against our shore. So it's a single tilt. So it's not like in the center of the current it's lower, but actually on the edge of the current it's lower. And we happen to be on the low edge. So as the current weakens, it would raise sea level here, if here is my elbow. And so the Gulf Stream is about, well, depends on where you are, approximately 30 spherodraps. Spherodraps are millions of cubic meters. One spherodrap is 1 million cubic meters of water per second. So there's about 30 million cubic meters of water per second going by our coast. 15 of that, half of it, is an overturning circulation, a deep overturning circulation that's part of global circulation, that will potentially slow down. And so I think the latest projections are like a 30% increase, or sorry, a 30% decrease. So let's say 5 spherodraps off. So it's something that's going 30, and we're going to knock it back to 25. So that's sort of it's not a huge change. And on top of that, then the actual amount of sea level change that tilt causes is only on the order of a few tens of centimeters. So it's less than a foot. The whole thing could stop, and sea level is only going to raise a foot at the most. So it pales in comparison with the ice problem. And that's something I try to emphasize. A lot of people are like, oh, we're going to get a little bit from this, and we get some from subsidence, and we get some from the tilting of the surface because of the currents. I'm like, but that's peanuts compared to when you melt 3 meters of ice. So I think that to me, as a geologist, I take the long view, and once that ice starts to go, it's going to go. We may not live to see it all, but do I really have to live to see it to prevent it from happening? So.
I just had a quick question. You mentioned that you analyze fossil corals. Have you done that with our deposits here along the Calvert Cliffs?
I actually have.
All right. How many species do we have, and how deep are they?
So I actually have to talk with Stephen about where those samples he gave me came from. But I have taken some bivalves from the cliffs and measured the magnesium calcium ratio in the skeleton, in the shell, and got little annual cycles. And it just tells me that there were annual cycles, which I knew there were to begin with. So I need to put it in larger context. And for that, I need really better age control. And that's another thing I need to talk to Stephen about, is about what is the state of age control in the cliffs? Because right now, I don't know. I have not delved deep into this because I'm soft money and I have to pay my salary. And so I have to go with getting grants that will pay me to do my work. And until recently, I have not seen funding sources willing to give me substantial amounts of money to work on this.
So
So
have
I
you-
played.
Okay. So do you see more than one species of fossil coral along the cliffs that have been given as samples?
So yeah, the fossil corals in the cliffs, I've mostly seen, I want to say Astrangia.
Australia.
Okay. It's written on my whiteboard in my office, but I don't. But it is not very good for the type of work I do. I've seen it's a branching coral, and when you break them open, they're often very sandy on the inside, and they don't have a real clear growth structure. And that's what I need in order to do the coral work. So I happen to have a piece on my desk of a coral that I do use. And so this coral, you can see the corallites. Oh, let's see if you can see it.
Yep.
Yeah, so you can see the corallites there. And this is a core through a 2.5 meter high coral head. The living tissue was right there, and we basically took a biopsy. This is all dead stuff, and it was 2.5 meters of dead material that we then can, with a dental drill bit, drill along those skeletal elements, the lines there. We actually target a single corallite, a little one animal, and its outer rim, and we go all the way down as far as we can on that rim, and then we'll switch to the next one. And we use a dental bit to do so. And then we take the powders and work up the chemistry of that. So
What depth do you think the corals in the fossil corals in the Chesapeake Bay were?
oh gosh, I mean, I would call it neritic. I mean, sometime somewhere on the shelf, they were small, so they could have been azoxanthelate. They could have been deep enough where they didn't need much light because they're small. So then I have no idea. Somewhere on the shelf, within 200 meters. That's all I can say.
Okay, thank you.
I think there's probably better estimates depending on where you are in terms of biological sourced depth. Yeah.
Are there any other questions? Okay, on behalf of the club, Hali, I'd like to thank you very much for sharing very interesting talk with us. It was perfect, geared perfectly for our group. And I really appreciate the effort that you've put into that for our benefit. Thank you very much. And thank you for the inspiration as to what we can do and what we can help to do to change the future.
Please. Thank you for inviting me.
Paul, do you have anything else on behalf of the club? No, I just wanted to say thanks. You know, you definitely kept this interesting, and you know, unfortunately, we are all becoming more experts at this. So, no, nice job. I'm glad to see the attendance. Did we have any other questions from anybody else? I saw most people were on mute, so we appreciate that during the lecture time. But we got a wealth of knowledge right here, so fire away.
Just one last comment. Our next Fossil Club meeting will also, actually our next two Fossil Club meetings will also be held in this format. One in September and one in November, as we usually do have at those times of the year. Our next speaker will be Dr. Bruce McFadden from the University of Florida. And we haven't set a date for that yet, but it will be in September. Just let me see if I have a date marked on my calendar. No, so I have to do that. But I'll be sending out a notice and an announcement from Dr. McFadden as to the topic for his presentation. And then just hold the phone here. And then for our November meeting, we're going to have a presentation by Emily Willoughby. And she is, among other things, just an absolutely superb paleo artist. And she has done, well, she's written a book, but this is some of her artwork that she has. She's just such an excellent artist. And I heard her presentation previously for another fossil club in Minnesota. And I was fascinated by it, and she has agreed to speak to us in November. So that's what's coming up, but you'll be kept appraised of that in the June issue of the Ecfora. So thank you all very much. And so I believe that probably concludes this evening's presentation. Thank you very much again, Hali. And thank you to everyone else who has joined the meeting this evening. So good night all.